Hello everyone, my name is Jing Zhao from CGCL and SCTS Lab. It's my pleasure to stand here and share with you one of our recent works, a structure-aware storage optimization for out-of-core concurrent graph processing. Here is the outline of the rest of my talk. First, I would like to introduce the background and challenges. With the arrival of big data era, graphs are widely used in many fields, such as social network analysis, commodity recommendation, transportation, and so on, because the data structure of graph has powerful expression ability. In addition, with huge demand of graph processing, a large number of graph processing jobs run concurrently on a common platform. This picture shows the variation of the number of jobs within 1 week traced from the real Chinese social network. We can find that more than 30 jobs are executed concurrently at the peak time. In particular, these concurrent graph processing jobs are usually handled on a common underlying graph to serve different products. However, most existing out-of-core systems are inherently designed to optimize the performance of individual graph processing job. When there are multiple graph processing jobs executing concurrently, they will suffer from significant high data access cost. The execution model of existing systems is shown in the left figure. We can observe that multiple copies of the same graph data are maintained in the memory and the last level cache and are individually accessed by the concurrently running jobs. Obviously, it results in inefficient use of data access channels and storage resources. To lower the data access cost toward high performance, as the right figure shows, several out-of-core concurrent graph processing solutions are designed. However, they still suffer from much unnecessary I/O traffic. Because existing solutions have to entirely load each graph partition into the memory for concurrent jobs, even if most vertices in this partition are inactive and may be shared by a few jobs, which leads to much redundant data access overhead. So entirely loading each graph partition within every iteration will incur much useless effort, and this wasteful effort is the main reason to slow down the overall performance. To prove it, we evaluated the performance of concurrent jobs on grid graph M over 5 real-world graphs. As shown in left figure, we can find that the graph data accessing time occupies a large ratio of total execution time, and the ratio increases as the graph size becomes larger. As depicted in right figure, there indeed exists significantly unnecessary I/O overhead. We attribute this phenomena to the real-world graph's power law property. Specifically, a small part of vertices are neighbored with most vertices, which require more iterations to converge than others. To prove this phenomena, we evaluated the details of the data access characteristic of concurrent jobs on grid graph M over CW dataset. As the top figure shows, we can observe that the ratio of active vertices drops significantly after a few iterations and becomes very low as the algorithms close to convergence. The bottom figure shows that a few vertices are frequently handled by concurrent jobs than others. Thus, the most ratio of the I/O traffic is carried out for loading the graph data associated with these vertices. Based on these observations, we propose and design a graph storage system, GraphSO. Now I will talk about it. In order to solve the I/O inefficiency of concurrent jobs, a fine-grained graph representation and a structure-aware graph repartitioning strategy are proposed. Besides, we also designed an adaptive graph processing mechanism and a structure-aware buffering strategy to further minimize I/O overhead. First, I will introduce the fine-grained graph representation. Taking each partition as an example, the original graph is first divided into 4 partitions for parallel processing. Then the static partitions are further logically divided into a series of chunks by traversing the graph once, and each chunk can be fed in the last level cache. During the traverse, A T-trunk table is established to record the information of trunks. Each entry of the T-trunk table is corresponded to a visited trunk and consists of 3 files. The first 2 files describe the ID and the start location of the corresponding trunk. The third file is a key value table to store the source vertices set and the number of their alt edges. Through this table, we can get the number of edges that graph processing job needs to process. Now, I will talk about the structure-aware graph repartitioning strategy. During the execution, Graph SO will dynamically identify the active trunks for different concurrent jobs, and based on this collected information, Graph SO adaptively repartitions this underlying graph by putting the active trunks of all concurrent jobs together into several logical partitions. By such means, the graph repartitioning cost is amortized by these concurrent jobs, and these jobs only need to maintain a single copy of the same underlying graph on the memory and the last level cache. To enable the loaded graph data to be shared by more jobs, Graph SO loads the most frequently used trunks preferentially. To achieve this goal, a priority is assigned to each active trunk to schedule their loading order. Is set by 2 rules. First, more related jobs and more active vertices. Second, higher average degree. To efficiently stream the logical partitions into the last level cache, the processing of trunks need to be synchronized for different jobs. Only when a streamed trunk has been handled by its related jobs, the next trunk can be handled. So we designed an adaptive graph processing mechanism. Graph SO will unevenly assign the computing resources to different jobs, according to their computational load. The computational load of jobs will be calculated according to computational complexity and the number of active vertices. Finally, in order to further reduce the I/O overhead, we propose an efficient structure-aware buffering strategy. Graph SO will build a buffer space in the main memory and judiciously buffer one copy of the common trunks in the buffer space to be shared by concurrent jobs. To enabling the cached trunks be effectively reused by more concurrent jobs, we customize an insertion policy and an eviction policy. When the buffer space is not full and the loaded trunks have not cached, these trunks will be inserted into buffer space. If the buffer space is full and the loaded trunk have not been cached yet, the cached trunk with the lowest priority will be evicted. This figure shows the architecture of our storage system. Its key techniques mainly include structure-aware adaptive graph repartitioning, processing, and structure-aware buffering. Besides, Graph SO uses a structure-aware buffering strategy to further minimize I/O overhead. Then, I will introduce the experimental results of Graph SO. Our experiments are conducted on a server, and 4 graph processing algorithms are used as benchmarks, including PageRank, breadth-first search, single-source shortest path, and weakly connected component. The right table shows the properties of the 5 real-world graphs used in our experiments. To evaluate the performance of Graph SO, we integrated into 7 popular systems. In our experiments, we mainly show the performance improvement when Graph SO is integrated into Grid Graph. Specifically, Grid Graph integrated with Graph SO, which called Grid Graph O in our experiments, is compared with Grid Graph M. First, we evaluated the overall performance of them. The left figure shows the total execution time of 4 concurrent jobs to different schemes. It shows that Grid Graph O achieves shorter execution time than Grid Graph M for all graph datasets. To evaluate data access cost, we then break down the total execution time in the right figure. The result shows that, compared with Grid Graph M, less graph data accessing time is required in Grid Graph O, especially when the size of the graph is very large. For example, the data accessing time of Grid Graph O is reduced by 4.6 times, compared with Grid Graph M over CW dataset. Next, we trace the total I/O traffic for executing the 4 jobs on various schemes. Left figure shows that, compared to grid graph M, less I/O overhead is produced by grid graph O, especially as the graph size is larger than the physical memory size. For instance, the I/O cost of grid graph O is only 21.6% of grid graph M over CW dataset. Besides, we also evaluate the volume of data streamed into the last level cache. Red figure shows that grid graph O streams the less data into the last level cache. For example, when processing CW dataset, the volume of data streamed into the last level cache in grid graph O is only 49% of grid graph M. This is because grid graph M streams the inactive chunks into the last level cache, while this unnecessary overhead is eliminated by graph SO. Then we evaluate the performance of various schemes to handle 4 jobs over CW dataset when using different sizes of physical memory. The results are depicted in the left figure. We can observe that graph SO achieves better performance improvement when the physical memory is smaller, due to its higher utilization of memory resources. In addition, we also evaluate the execution time of 4 jobs over various schemes on TW dataset, and changing the number of CPU cores. We can find grid graph O outperforms grid graph M under any circumstances. We also integrate graph SO with other frameworks. This table describes the total execution time when running the 4 jobs on various schemes of different systems. The experimental results show graph SO achieves considerable speed-ups in comparison with graph M over all of the datasets. Besides, we evaluate the performance of C-graph to further demonstrate the efficiency of graph SO. This page shows the evaluation of pre-processing cost. We can find that little additional time is required by grid graph O to generate the T-trunk table. Besides, the extra storage cost is also small. Although graph SO requires little extra overhead, much unnecessary I/O traffic can be reduced by it. Now, let me conclude. First, we disclose the significant I/O inefficiencies of existing out-of-core concurrent graph processing solutions, and observe that it is the main problem which slows down overall performance. Then, we design an efficient structure-aware adaptive graph repartitioning and processing mechanism to solve the problem. Finally, we propose a structure-aware buffering strategy to maximize the utilization ratio of the graph data and further reduce the I/O overhead. In future, we will research how to optimize our approach to efficiently utilize the SSDs to serve the execution of many concurrent graph processing jobs. That's all of my presentation. Thank you.